All right, let's talk very briefly about water quantity. So we're going to talk about quantity and quality in this class. And quantity is going to be the one that's going to help us design the size of our treatment plants. So the biggest equation or the biggest concept that you need to know when it comes to designing is water demand. So water demand is the total daily consumption divided by the total population. So this is a number that will be in gallons per day or liters per day, depending on where you are in the world. Normally we see the unit MGD, which means million gallons per day in the United States. If you're designing for other countries, you'll tend to see liters per day. So there's two basic things that you need to know when it comes to water demand. You need to know the population served, the number of people, and you need to know what's called the per capita water usage, so the number of liters per person per day that is used in a specific population. So in general, we use average daily consumption over 1 year to design water treatment plants. But it's also good practice to look at the maximum, the minimum, and look at monthly, weekly, daily, and hourly data if it exists. It doesn't always exist for every population that we design for. So good practice to use average daily consumption over a year, and then if we have more granular data, we use that. So really quick, to kind of put this in perspective, we have this cycle, right, that we showed on the first day of class where we have source water, we have treatment, we have users. And I just kind of want to point out where demand lives on this particular graphic. So demand is generated by the people who are using water. So not only your customer base in terms of a population if it goes to somebody's household, but also industry and firefighting flows. And so demand is driven by end users, right? That's water usage patterns. So that's important to remember. So two important things for water demand, right? It's population and then the per capita water usage. So we need to be aware of what we call our design population. So the design population is basically the future population that must be served by the water or the wastewater treatment plant. And it's most of the time going to require us to try and forecast the population forward into the future. So we can use sources of data like the US Census Bureau, we can use water system utility bills, a number of connections, school enrollments. There's many different sources of data that we can use to find population. And then you can pause this slide to kind of take notes on each of these different methods. I'm not going to quiz you on the specific methods. It's just kind of good to know how you could forecast population. Population doesn't tend to increase linearly. It tends to have different shapes as it increases. So there's 4 different methods that you can see for population growth. So there's what we call a logistics population growth, and so this is going to model population based on what we call an S-shaped curve or a sigmoid curve, and then we basically take a startup period, and then we have explosive growth, and then it tails off, and we'll show a graph of this on the next slide. We can use what we call the constant percentage method, so the rate of growth is proportional to the population, so this is more of a linear style of growth, but it's still a sigmoidal curve. We can use what's called an arithmetic method. So the rate of growth is equal to a constant. So this is going to look more linear as well. It's basically estimating the middle point of that sigmoid curve. And it's basically the idea is that the upward trend in population is generally linear. And then we can have what we call a declining growth method. So the rate of growth mirrors what we see when we kind of reach that asymptotic number, so when that graph starts to flatten out. So let's take a look at that on a graph so it's a little bit easier to see. So what you see on the left side uses the logistic method, and it shows you all the equations for the logistic method. But let's take a look at this curve. So this is what we call a sigmoid curve. So you have a little bit of time where you're starting to grow your population, and then it explodes, and there's linear growth in this center section. And then it asymptotically comes up to a value, so it means it just approaches that value, right? And so with each of these methods, what you're going to see is that there's different equations for each. We're not necessarily going to go through and do forecasting of populations. I'll give you population figures most of the time in class, but it's good to be aware of these if you're going to be designing in the future. So you'll see that the logistic method, population is based on a lot of different constants, and it has exponentials in it, and that's important. You'll notice with the constant percentage method, you still have that exponential growth. There's still logs here, but it looks kind of like a first order equation, basically, is what happens here. With the arithmetic option, it kind of looks like a zero order kinetics reaction, right? Your change in population over time is related to a constant. And then your declining growth method basically takes what we call a saturation population. So it's the population that basically you're going to approach on that sigmoid curve. It's the max population you're going to have in the system. And it bases our population growth based on that saturation population. So just 4 different ways of estimating population and forecasting. We're going to focus primarily on the calculations for demand, so I'll give you population, but it's good to be aware of these as an engineer because you will have to forecast population when you design. We don't design things for today, we have to design things for the future, so you have to be aware of the population. So water demand has 2 components. It has population, but it also has water usage. And so I like to throw up this curve, this pie chart, to show you how much water we use. So this comes from the Water Research Foundation. It's posted on the EPA's website. This is how we use domestic water, so at your home. So we have clothes washers, we have faucets, we have showers, we have toilets. We could potentially have leaks in the system. Unfortunately, our infrastructure is aging, so we have lots of leaks in our system. But you can see that it's not just for drinking, right? We use water for many, many different things, and we have to account for all of those different usages when we have that per capita number, right? The liters per person per day. So we'll go through some detailed tables in class of what water usage looks like and how to calculate it. But I want to put this up to really emphasize the point that we don't only consider water for drinking water uses. We consider it for all uses. And then I really like this graph because it shows the domestic water use per person per day based on population growth in certain areas. So you'll see that we're starting to use a lot more water out west, which makes a lot of sense if you know what's going on out west in the US right now with drought and changes in water patterns. So areas that are getting built up in Utah, for example, are growing extremely fast and they're using a lot of new water. So it's kind of interesting because it shows you, as the United States has been growing, how much our water use has been changing. And then the last thing that I want to talk about here is design capacities. So once we know our water demand and we know the average daily flow, that kind of thing, there's many different ways to calculate that flow. Do we want an average? Do we want a min? Do we want a max? Where are we looking at this? So things like if your source is a river versus if your source is a well, we might want to use the maximum flow, right? So we might use the highest flow possible, the highest demand possible. So that's something to be aware of. If we're looking at our low lift pumps, we're going to want to look at a maximum daily water demand plus on average about 10 to 33% of the pump capacity, right? Because we can't have all the water go to zero in a pumping system or the pump burns out. So take a second and pause this. We'll talk about this more in class. What you'll see here is that different components of the water system are going to require different water quantities, different flows, and they do different calculations. And you basically need to use these different areas of the water system to calculate the water quantity that you're going to need to design your treatment plant for. So we'll talk about this in more detail in class, but that's just kind of a very brief overview of some topics related to water quantity that we're going to talk about in more detail.